Hello, everyone, and welcome to another episode of Let's Talk ETC. Today, we're going to be talking about formal methods in software and specifically in smart contract design. And I have an illustrious guest with me, Dr. Duncan Coutts from Input Output. He's been doing a lot of work in formal methods for software, for blockchain smart contracts. And he's going to enlighten us on the latest, greatest methods and tools. So welcome, Duncan.
Thank you very much. I'll do my best.
So for the people that don't know, you were on the show, gosh, it may have been almost 2 years ago. And that was
it's been a while, isn't it?
Yeah, and that was one of the most widely viewed shows. So there's clearly a desire to learn more about formal methods and how to secure smart contracts. Every time people hear about a hack that loses 100 million, or not 100. Well, yeah, there have been $100 million ones, but
there's a nice website of how many days since the last $100 million loss, isn't there?
Okay,
that's a nice one.
Yeah. So this is obviously something that's important, as forced upon us, whether we were a math type or not. But yeah. So anyway, so that's why it's great that you're doing the show with us. So for the people that don't know, why don't you kind of give us a little bit of your background and how you got into this field?
Sure. So my background is in computer science. I did a PhD in computer science, and particularly in an area of programming language design. That is, it's a whole school of thought on how should programming languages be designed. So it looks at a whole range of like non-mainstream languages, and in particular, my interest was in a group of languages called functional languages, and Haskell is probably the most widely used of the more pure end, of the more extreme end of those functional programming languages. So then the last 10 years or so, I've been running a consultancy company specializing in Haskell. And the last couple of years, my colleagues and I have been helping IOHK with the development of Cardano.
Okay.
And I've ended up as the chief technical architect, and that's my current job title.
Okay.
On behalf of IOHK for Cardano.
All right, very good. Now, I'm curious about your consulting business. So do people come to you, and people that need the software has to be right? And so that's the people that come to you and they want...
Yeah, so the customers that come to us are people that are using Haskell already for whatever reason, or are thinking of using Haskell. Okay. And then they just want additional help with that. And we've always specialized in Haskell and then helping people to use it. And people use it for all sorts of different reasons. And actually, it's not that often that people want to use it for really doing stuff very rigorously. They usually simply want to use the benefits of Haskell to do things at an equivalent level of quality, or maybe slightly better than mainstream, but do it much quicker. So
okay.
The way I sort of see it is that Haskell is a real improvement in the trade-off between quality and development speed. But people often simply use that real improvement to do development quicker,
right.
Cheaper,
Yeah.
And it's not that many customers that come along and say, right, we really want to achieve like high assurance.
Okay. Do you think they'll ever get to a time where people will come to you and say, we want you to use all the formal methods you have to make this software?
Well, that's almost what we're doing now with Cardano, right? So, and that's why blockchain space is, in my sort of view, quite an interesting opportunity for this kind of application of these approaches it's an area where you really do care, you really do want to build software correctly, because there's a lot of money at stake.
Yeah.
And so, and it's particularly, the like with the fact, the $100 million hacks all the time. It's been demonstrated. It's obvious to people now that people will steal your money before you can fix the bugs. So you have to make sure there are no bugs in the first place. And
right.
So then you need all of these approaches from computer science of how do we ensure that our software does what we intend it to do, and therefore that it does not have these exploits and bugs and whatever, because you can't fix them afterwards.
Right. That's true. Yeah. I mean, I don't know who these people are that think about all these exploits. I mean, the one that breaks my heart is there was the Ethereum classic, the classic Ether wallet, and somebody somehow, I think it was a social engineering attack, and they messed with the DNS settings, and so I remember some people lost money. So there's just people out there. Somebody's just thinking about all the ways they could break these systems, and
Yep.
Yeah.
Which is why the job of the defender is very hard, because you have to defend against all possible things, whereas the attacker only has to find one weakness and exploit it. Right. And that's why you need to do this stuff in an extremely systematic manner. And that's why just thinking hard isn't enough. You have to, if you really want to achieve this, you need to do this in this very systematic way and establish what are your security models? How do we really demonstrate that what we've done does what it's supposed to do? That doesn't allow for any of these other things.
Yeah, yes. Go ahead.
Social engineering attacks are quite hard to deal with, I mean, in some sense. But at least we can deal with the ones where the software is obviously wrong. The ones that involve computers and humans together, requires a bit of computer and human in the solution. So my focus is really on the bits where the software can be said to be either right or wrong.
So that would be another layer of having of worry, right? Dealing with the social engineering component, definitely. Security. I agree with what you said. It's really hard. So if you had a mansion that had 50 windows and you remembered to lock 49 of them, right? If you just leave one window open, an entire army could get into your house through one window. So it's just so unforgiving. You just absolutely have to do everything right all the time.
Absolutely. And that's why you need to do these things systematically, and you have to, because it's too complex to just sort of think and hope and test. That's why you need this higher levels of formality, why you need to apply techniques from computer science that computer scientists have been working on for the last few decades, but the mainstream industry just doesn't apply them because it's too expensive, it's too difficult.
Right.
Well, here's a case where it's worth it,
Yeah.
And many of them aren't as hard or difficult as people sometimes make out. I mean, yes, okay, it's not trivial, it's not easy. It is extra work, but it is tractable.
Well, here's something that shocked me. So before we get into blockchains and smart contracts, so I've been trying to write a little compiler just to teach myself that programming field. And I asked a question to Eric Scott Raymond. He was a famous open source figurehead. And in order to check your compiler, you would need to use formal methods, but nobody really deals with, if you're making up a new language, you don't have the time or necessarily always the interest to do that. So you basically just use trial and error and hope everything's going to work out okay, and your compiler doesn't have huge security bugs in it. Eric Scott Raymond agreed with me. I think whatever his middle name is, Eric S. Raymond. I don't know what the S stands for, but he said, you just pretty much do trial and error because using formal methods is too hard. And so that got me thinking, oh my God, are you telling me that all these languages people develop where they throw together a compiler, they're not specified and they could all have all these security issues?
So that's kind of half true. And I don't want to beat up on Eric, but he's approaching this from so what he's saying is sort of true of the engineering school of compilers, but it's not actually true of the computer scientists school of compilers. So, and this again contrasts with the kind of mainstream engineering approach to programming languages and the academic approach. The academic approach is much more rigorous. It can specify things mathematically. It's not just build it and hope. I mean, maybe the GNU-C compiler and LLVM and all these others are built in that way. That wouldn't surprise me. But but the people who take a slightly more academic, slightly more formal approach to these things, it's a lot better. It's not perfect, but they at least specify. Very often they specify their core languages in a very precise mathematical way, and many of these things get published. And often those get coded up in theorem provers and other sorts of tools to mechanically check certain properties.
Right.
So people have proofs of, this type soundness, or the evaluation, preserves typing, and all kinds of different kinds of properties that you would want in your language. Now, all that said, even the academic languages, even though they might prove things about their language, that doesn't actually mean that they prove things about the compiler very often. So many, even research compilers, don't have a proof that their compiler is correct. That is very unusual to do that, but it's not completely unheard of.
Yeah.
There is actually a project out of INRIA in France where they did do a full, most of a proof of a a somewhat optimizing compiler for C, and that was proved using the theorem prover tools out of INRIA, and that was a major project. That's called CompCert. So it's a verified C compiler, but that was very unusual. I mean, because it's a serious compiler for a serious language. The state of the art otherwise is more that you prove things about the language, but you don't actually prove the compiler.
Right. So do you think the typical way these things go is somebody throws together a language, and then a couple years later, if it has traction, then people develop a formal specification, then the academic community might try to formally specify it, but you had all those years while it was gaining traction where it wasn't checked and verified. So how many years did the language C exist, and how many years was it passed around the academic community?
Yeah.
Before.
No, that's a very good question. So again, it comes down to there being two approaches to this stuff. One is specify first, and one is specify afterwards, and one of them is better than the other, right? So the mainstream engineering approach is like C or like JavaScript. You build a thing, and then if it becomes interesting, then later down the line you might have some academics to go and try and specify it. But that's really the wrong way around to do it, because it's so much harder that way around. By the time you've built the thing without the benefit of having written a specification, try to reverse engineer that specification. It's going to be ugly,
right?
And it's going to be awkward. And they are. People have written formal specifications of C, C++, Java, JavaScript, but they're huge and complicated. Whereas if you take the approach of writing a specification at the same time you're designing the language, you can make changes to the language to make the specification simpler. And then you end up with, or you can end up, if you take that approach, you end up with something a lot simpler and with a much simpler specification. And actually the language often ends up being better and simpler as well. And you often end up with a better design by having one with a smaller, simpler specification. So that's these kind of two schools. Do the specification at the same time as the development, or do it afterwards. And if you're interested in the specification, doing it at the same time is just so much better. Right. Hoping that you might get one afterwards is a fool's mission.
Yeah. All right. So we've used this term formal methods already a couple times. People might not be aware of what that means. Can you kind of give a very gentle, basic introduction to what it means to use formal methods in software and smart contracts?
So formal methods in general is about taking the approach that programs are mathematical objects and can be reasoned about using mathematical techniques. So, which is in itself a radical idea, right?
Right.
So, when you first come across programming, you might simply think that programs are just things, and they have no, they have no connection to mathematics at all. Oh, well, okay, they've got plus and minus and whatever.
Or if they're a nerd like me, if they're a nerd like me and they know about Alan Turing and Kurt Gödel and Gregory Caton and their work, and so then they might know about a Turing machine so they might know that. But yeah, maybe a lot of people.
But when you're writing a program, do you really think that program is a mathematical object like high school algebra? Most people don't think about that, and that's because most mainstream languages, that's not really true. They're not simple like high school algebra is. Whereas, but if you develop languages in a particular way, then it is possible to have programs be mathematical objects that are simple and can be reasoned with and manipulated using mathematical techniques, because the description of the program is in terms of mathematics, like say set theory or something like that.
Right.
And so then you can actually make statements about programs and then prove statements about those programs. You actually write proofs, not just hand wavy informal ones, like the same quality of proofs that mathematicians write, and that are real honest to goodness proofs.
So that makes sense why you would be interested in functional languages, because every language in principle has a mathematical structure to it, a formal method or formal structure. It's just
formal
that
description. Yeah.
Formal description.
Yeah.
It's just that functional languages are the ones.
A much simpler one. Yes.
Yes.
Exactly.
They're practical. They're tractable to work out, to deal with the mathematics.
Yes, and they're based on a simpler mathematical description approach as well, which is based on mathematical functions.
Right.
Which
Yeah. Okay. Well, then this is something I've been wondering about. So if functional languages are so wonderfully mathematical and you could prove things about them, how come? Is it just a historical accident that functional languages didn't take off? Or why do we live in a world where we have C++ and JavaScript?
Yeah. No, that's a great question. So it really comes down to the history of this stuff. So if you go back to like the beginning of computers, like you mentioned Alan Turing, these two schools of thought on how to program computers goes back to that time. So Alan Turing's Turing machine is a mathematical description of a hypothetical machine, but you can see it's kind of very operational. You could kind of, when it says that there's an infinite long paper tape, but you could imagine, a physical machine that was like Alan Turing's, abstraction description of a computer. At the same time as Alan Turing, there were other mathematicians and logicians who were looking at the notion of computability. And they looked at it from a completely different view. It was all just squiggly symbols on pieces of paper. It was nothing like, a hypothetical, imagined, but physical machine. So
this is like Alonzo Church and lambda calculus.
Exactly. Yeah, and that's lambda calculus and all that stuff. But the sort of Turing machine style computers became practical, during the 1940s and 50s. And then how do you program those machines? Well, you program them in the way that they work. Because they're so expensive and so slow, you really have to program them efficiently. And so you have to program them, using assembly or machine code in the way that those machines actually work. And then people built up programming languages as just better and better ways of imperative programming languages, as better ways of programming machines in the way that they actually work. Whereas this other school of thought said, no, computation is all about this lambda calculus and functions and all that. It's all got very nice, beautiful mathematics. But that took a lot longer to become practical, like decades longer to become practical, to the point where you could program a computer and have it run in a reasonable amount of time. And so it really relied on two things. It relied on computers becoming fast and cheap, so that programmer time became much more important than CPU time, and also relied on compilers for functional languages becoming much, much better. And that didn't really happen until the 80s.
Oh, okay. So if von Neumann and the early people that designed computers, if they would have somehow made something closer to lambda calculus, closer to the functional programming paradigm, it may have taken off sooner.
Maybe, yeah, but it's not totally clear that really would have been the case, because it's not clear that you can build machines that work in the style of the lambda calculus and have them be efficient. I mean, people have tried that actually. People have tried building, lambda calculus reduction, bits of silicon, but they don't actually work out all that well. I mean, our current way of building CPUs is not bad. It's just that we needed a way of compiling from lambda calculus style languages into machine code that runs on classic chips, and that's what Haskell and other languages have solved as a research thing during the 80s, of how do you efficiently compile these funny looking languages into efficient machine code.
I see. So I don't know are you familiar with like the Lambda papers and the Lisp machines, and how there was a school that tried to do what we're saying, make I guess even the hardware that was focused, just on this stuff. Yeah. Okay,
but it didn't really work out all that well. It's not clear that it really ever necessarily would, even if history had gone slightly differently, or if maybe more money had been put into it. I mean, you could probably do slightly better than our current chips, but it would just be like tweaks around the edges. I mean, the way that RAM works and the way that all that sort of stuff, it's not obvious that you need to do something radically different for lambda calculus-based approaches. And what we demonstrated in the 80s, I say we, I mean predecessors in my school of thought, demonstrated was that you can compile lambda calculus-like languages to traditional machines. It just took a little while to figure out how to do it.
Oh, okay. So then I assume that the speed of good Haskell code then is comparable to the fastest imperative C++, Rust.
So it used to be that we all were targeting C as like the reference, because that's what everybody used to care about. But then like Java came along and Python came along, and sort of the bar got lower and lower. So getting performance on par with C is still quite hard, but beating Java or Python is a lot easier. So well-tuned Haskell code should be getting within maybe a factor of 2 of C code, but it should be on par with Java, and it should easily be beating Python.
Okay. All right. So assuming somebody wants to jump in, so they use a nice formal or a nice functional language that they could reason about mathematically. So then if they do that, then their code, they could presumably do some more verification that it does what they think it's going to do, and then they could make a lot of progress then in terms of security.
So this kind of stuff is not just a matter of using the right programming language. You also have to, Haskell is not a magic bullet, right? You don't just suddenly start using Haskell and all your code works. The most important thing about the full methods kind of approach to things is being able to capture your intention in a formal way. And that might be Haskell sometimes. In simple cases, you might be able to express your intention as a Haskell program, and that be sufficiently small that everyone can look at that thing and agree that that is right. And then you can then use some kind of method to demonstrate that your real program is equivalent to the specification that you wrote in Haskell. But more typically, you would be wanting to have some other kind of external, small, easy to understand, easy to reason, easy to argue about mathematical specification of what you want. So this is about capturing your intention, and this is actually, in many ways, this is kind of 2/3 of the problem. Capturing precisely what it is you want is really the starting point, so that you can then have any kind of hope of demonstrating that what you've done is equivalent to what you wanted.
Right. So I'm glad you said that. Is this correct? So for the people that are listening, so there's, can you break it up into 2 stages? So you have a problem you want to implement a piece of software for. So the specification, formal specification, that's phase 1 or step 1. And then implementing that formal specification then is step 2 or phase 2. So those are the 2 big bins that we could put the work into, specification and implementation?
Yes. Although in reality, it's a little bit more messy. In principle, in principle, yes, you sit on your ivory tower and you think very hard, and then you write down the perfect specification, and it comes out fully formed, and then you give it to a bunch of programmers, and they go and implement it, and then you test or you prove that your implementation corresponds to a specification. But the reality is a bit more messy. If you're actually wanting to do this, what you need some kind of design. You might have some very high-level, fuzzy requirements or business requirements, because very often you don't start with a problem that's very easy to specify.
Right.
So you have to start by all right, you take your English language written description of, very fuzzy, imprecise what you want, and then you do some prototyping, you do some experiments, you try this, you try that, you try to find what are the structure of things, so that you can even say, well, what are the mathematical objects in this space? What is it, the thing that I'm trying to reason about? What are they like? Like if you're dealing with blockchain stuff, you need to have a slight start with some understanding of what is the UTXO approach to things, to currencies, before you can really start writing detailed specifications.
So it sounds like what you're saying is you might even do some quick programming on the road to getting the specification. Maybe you throw like a Python prototype or whatever your favorite language, slow language is.
Well, of course I would do it in Haskell, but yes, absolutely.
Yeah. And then that kind of organizes your thoughts, and then you go back and do this formal spec, and then you go and implement it again, maybe even.
And actually, yes, and then you actually in practice you do multiple iterations. So, like for example, with what we are doing at the moment, or what we've been doing, recently, we're more or less at the end of this phase at the moment. Is with the specification for the rules of the ledger for Cardano. What objects go on the ledger, and what are the rules for when they're valid?
Okay.
We haven't. The way it went through was it was an iterative process where we would write down draft rules in this formal mathematical style using set theory. So a PDF description of our rules. And those would just be a draft, and we would sort of then sit around and think about it and argue about it and try and understand what it meant and say, what about this? What about that? And so you go through multiple iterations just by doing internal peer review. And then you also do prototype implementations of that. So not a full-scale implementation, but ones that just do the minimum to execute what you have in your specification. We call it an executable specification. It's sort of the equivalent of what you've got in your PDF version, but actually runnable. And you use that to sort of try things out and see if it can catch certain errors that you might not notice otherwise, and it can give you some feedback. And you can use that as a way of seeing whether your design was sensible. And then so you can go through multiple iterations like this of tweaking both. So both changing, adjusting the code, adjusting the specification, thinking about it, reviewing it with other people, until eventually you come to something where you're fairly happy with it. And one of the important ways of checking that it is sensible is by thinking about properties that the system should have. This is a very good way of getting a sanity check. So, for example, in a cryptocurrency system, it's a very nice property to have to say that after every single transaction or every single object that goes on the ledger, the total amount of money in the system remains unchanged.
Right.
It's very easy to get that wrong. Right?
Yeah.
But if that is right, that's a very good cross check that lots of your other bits of what you've done, are sort of self-consistent in some way, that you've not made some silly error. I mean, you need some things you need to just review by looking at them and thinking about them to say, is this what we want? Because you can have a whole bunch of mathematical rules that are self-consistent, and the mathematicians can tell you, these rules are definitely self-consistent. These are it's a perfectly fine mathematical description of a thing, but is it a description of the thing that we want?
Right.
And for that, you just have to have some idea of what you want.
Okay. Now, speaking of specification, so for the people that are following, so specification and implementation are two ways to think about the parts of getting secure software done. Yep. So the implementation part, probably people listening have all programmed in some language, or if they haven't, they know where they could learn a YouTube video or whatever. And so that probably they're familiar with to some degree. The specification part is probably what's new to them. Now, I was excited. I've done a previous show and I've done articles about TLA plus. There's what's exciting is there's tools to help with formally specifying your intentions for your code
and checking properties.
and checking properties. And if for people that are skeptical, there's even data points like I think Amazon and Microsoft, a lot of these big companies have gotten huge wins from using TLA plus and code like that. So you can't deny that this is great to catch subtle bugs. I think there was a big one on the Xbox that they caught using the TLA plus. So I'm curious if you use TLA plus or something like that. What do you recommend for that? That's probably new to some people, that specification. What tool sets to help with that?
Yeah, so we don't use TLA plus, but we use similar things.
Okay.
So TLA plus is a nice tool, and people who've not done any full methods before, I would indeed recommend going and looking at the videos and looking at some of the documentation, because it's quite a nice way into it, and it particularly works. It is more designed for imperative languages, and that's what most people are familiar with. So it's actually a good place to start. But partly for that reason, that's not what we use, and we also use some tools that are a bit more powerful than TLA plus, but correspondingly require more background and more experience with formal methods, and things that are a little bit harder to get into, like theorem provers.
Okay, so the tools that you use, are these kind of your own in-house, or are these?
No, generally not. So there's really a kind of there's two main approaches that we're taking. Okay. One is the kind of very full methods heavy, absolute proofs with theorem provers, and the other is a much more lightweight approach, which is much easier to combine with fast-paced development and sort of prototyping and iterative approaches.
Okay. Is there any tools that are like TLA plus that you want to throw out some names for if people want to research further? Any open source or proprietary?
Absolutely. The main thing that we use is a library called QuickCheck. So this is actually a testing library. It's not a library for model checking or theorem proving. It's a library for systematic random testing, but it's extremely good for checking properties. It is a property-based testing approach where you write the properties that you have written in as part of your specification. You translate those properties into Haskell or whatever language your QuickCheck library is for, because there are QuickCheck libraries actually for many different languages. It was first developed for Haskell, but it's been ported to many other languages now.
Okay.
So you write your properties in the language, in our case Haskell, and then you use this approach for systematically generating random input values and then checking your property is true for all of those values. And although it's a testing method, it's actually an extremely effective one for finding subtle bugs and for not having to do that much work for the testing. The number of tests that can be run versus the number of amount of time you had to think writing these properties is enormous. The sort of benefit to effort ratio.
I see what you're doing. Okay, I did read about this. So what you're doing is QuickCheck is using a brute force method. It's just throwing a lot of inputs and trying to break the code and just randomly searching the space to find issues, which is a great idea.
When you say break the code, it's not just break the code. It's checking that interesting properties hold. So like I said earlier, the property that after every transaction in the ledger, the same amount of money is present in the system. Right. That's a property that we can check. It's easy to write down that property. The sum of the money there's money in various different pots in the system, like the UTXO and the treasury and whatever. But if you add them all up, they equal one thing, and the sum of it before and the sum of it afterwards ought to be equal. It's quite easy to write that property down. It's a few lines of code. Right. But then the interesting part is, well, how do you check that property? How do you test that property is true? Because it's supposed to be true for all possible ledger transitions. Right. Any valid starting state of the ledger and any possible transition. So that's where you need to write these generators that can produce valid blockchains. And so we have invested quite a bit of effort into writing systematic generators that can generate random, valid, and invalid blockchains. And that lets us then test these properties against vast numbers of these things. And that gives you very, very, very high confidence that the properties are true.
Wait, when you say generator, you mean it's something to generate random values to input values? Is that what you're saying by generator?
Yeah, exactly.
Okay. Okay. Now, the issue with what I'm calling brute force checking, though, is if your inputs, your parameter space is so large, right? It could be so exponentially large that you're only going to check a small piece of it. And how do you know there's no corner case where, right, if this value is 0 and this value is negative, et cetera, you might miss that one. Your QuickCheck program might not pick that one.
It's true. The testing is not an exhaustive. It's not a fail-safe approach. But if you do it in a reasonable way, and there's lots of known techniques for how to do this, it's actually remarkably effective. It's not guaranteed. Testing is never guaranteed to find all cases, but given the experience, and not just our experience, but the experience throughout the industry has demonstrated that it's actually extremely effective, okay. even though it's not completely 100%.
So then maybe if somebody doesn't have the time, patience, or interest or funding to do the full formal proof that their smart contract is correct, do you maybe just using QuickCheck?
Yes, absolutely. Yeah, it's got a very high benefit to effort ratio, whereas the very formal approaches have they can produce higher assurance results, but they're a lot more effort.
Right.
And here's another data point, which is that the kind of people who really do go and do these formal proofs, they do QuickCheck it first, because QuickCheck finds 99% of the bugs, so that you don't have to try and prove things which it turns out to be not true.
Okay.
Finding bugs by trying to prove there are none is very time consuming.
All
whereas if you can basically eliminate all the bugs first by using QuickCheck, and then try and prove the properties that you already have very high confidence in, that's actually much faster than trying to prove it 5 times, and the first 4 times you do it, you find bugs, right, and you correct the bug, and then go and try and prove it again. And
so for the people that are listening, right? Okay, that's certainly one thing they can hold on to for practical, secure smart contract techniques. So QuickCheck.
So we call that a semi-formal method. So it's okay. Because you are using kind of mathematical notions in how do you describe the property, what property is it that you want, but then the checking of that property is not done by proof; it's done by testing.
Right.
So that it's one of these category of techniques that we call semi-formal.
Now, you mentioned specifying properties for your Haskell code. Is that something that you do in Haskell? Does Haskell provide a vehicle to specify the properties of your code, or is that some other language that you're using for that?
So with the stuff that we use for QuickCheck, then yes, it is specified in Haskell.
Okay.
And Haskell is a very nice language for writing things about Haskell, as it turns out.
Okay.
So that actually works reasonably well. Now, for our specifications of our rules for the ledger, it's very important that a specification language be something that's comprehensible. And I'll admit that not everyone can read Haskell and see a Haskell program as a specification. So we don't specify the rules of our ledger using Haskell. We specify them in a PDF document with lots of mathematics. And the language that we choose there is set theory, which is a very standard, common mathematical notation and formalism that a large number of people are familiar with.
Right.
Lots of mathematicians, lots of people in physics or other kinds of technical disciplines. They use set theory for lots of things. People have done a kind of undergraduate level of mathematics will have done set theory.
Okay.
So that's why we use that language. As our specification language.
Now, I did want to also ask you for, maybe this is a good segue. So I wanted to ask you about the current work you're doing on Cardano for input-output. And the segue is, you're talking about QuickCheck and how it's law of diminishing returns if you want to take that next step and formally verify to get that last 1% of confidence in the correctness of your code. Is Cardano and the work IOHK doing, are they doing just QuickCheck, or are they doing all that effort for that extra 1%, that extra bit of confidence?
We are taking a kind of 2-speed approach.
Okay.
That we do the lightweight formal methods, the semi-formal stuff, so that we can get things deployed and get things working. But we are also following up with the higher assurance approaches. So that's not just using QuickCheck, but using proper theorem proving tools to prove things about the code. And I haven't talked about that yet.
So why don't you kind of elaborate? I'm sure it's really interesting stuff. What you're doing specifically on a day-to-day basis for Cardano and for input-output.
So the major effort where we have been applying semi-formal approaches and formal specification is with these ledger rules. So what exactly are the rules of what makes a valid ledger or valid blockchain? Because that's so important for implementing the thing correctly. So we spent a long time doing this kind of iterative internal peer review approach to specifying the ledger rules using a set theory approach, and we've published those specifications for anyone else to see now. We published them. It's on the IOHK blog. We published them around the time of the IOHK conference. So those give this set theory description of what is a valid blockchain or a valid ledger for both the Byron era and the Shelley era, which is the new version that we're moving towards. And so that's being transparent. Anyone can go and look at it and see, do they think we've made a mistake? We can get further peer review. It explains some of the properties that this should have. Then, in addition to that, as I say, we also have an executable version of the same.
Okay.
And then we have the real implementation. And we then use QuickCheck to test the real implementation against the executable version of the specification. And so that gives us very high confidence that our implementation does the same thing as our specification.
Now, did I hear you correctly? Are you saying that you're after you have a formal specification, it automatically implements it?
No, it's not automatic.
Okay.
And this is actually an area where better tool support would be better. But we deliberately chose to use just simple set theory as our specification language, rather than using, let's say, a tool like TLA Plus or one of the theorem prover tools, because we wanted to have something that it was very easy for other people to read and see that they agreed that this is indeed what we wanted.
Okay.
So that we were optimizing for readability. Now that doesn't mean that we won't ever go and use a dedicated tool. We do have some ideas about how to do that slightly better in future. But I think optimizing for readability of specifications is very important.
Sure.
So what we did was, we had a readable PDF specification, and then we have an equivalent Haskell executable version. And that's a slight weakness in the system, where you simply have to inspect the two side by side and see that they are the same. But that said, it's not that hard to do.
Okay. And now, after you do these semi-formal methods, and you said you're going to go beyond that and try to do fully formal methods, or whatever you call it. So you are going to be able to get to the point where you can say, okay, Cardano is, knock on wood, we're supremely 100% confident that there's never going to be any issues with people's money on this blockchain.
So I would never go quite that far, because you have to. That's a very, very strong statement. But our approach is increasing levels of assurance, which is and corresponding to increasingly high qualities of evidence of assurance, and evidence covering a wider range, larger parts of the system. So the ultimate, in the limit, yes, you could in principle get towards that kind of 100%. But the intermediate stages are that we have applied semi-formal methods to this component, which is really important, but we've not done it to other parts which are less important, or we've done it to this part with this level of assurance and this quality of evidence, and then a few months down the line we move up to a higher level of evidence and higher quality. So it's an incremental process of getting more evidence, better quality evidence covering a wider range of parts of the system.
Okay, but you don't think you'll ever get to the point, or do you, where your job will be ended? We're like, okay, we've checked everything, we've proved everything we possibly can.
I suspect the rate of change in the cryptocurrency industry is such that there won't be much danger of running out of things to verify here.
Oh, okay. So because of the things change, that's going to keep you busy.
I would imagine so. Yeah.
Okay. Well, then Bitcoin doesn't change much, if ever. Could somebody conceivably, make it absolutely, publish a proof that this code?
Probably, but they'd have to rewrite it not in C, I would imagine.
Right. Okay.
They'd have to reverse engineer a specification, and then do an implementation of that specification in a fairly formal approach.
Okay. And so, all right. Yeah. All right. Very good. So I think we've given people a pretty good introduction, people that didn't know anything about formal methods. So they learned about semi-formal methods where you specify your properties, intentions. We talked about QuickCheck. We talked about TLA plus. We talked about using languages that are amenable to mathematical analysis, like functional languages like Haskell. I think you've given people a lot to chew on. Is there anything else you want to add before we close?
Maybe one last thing would be, we didn't actually mention the theorem prover stuff. And I mentioned theorem provers a few times, but I didn't say in really any detail what.
Oh yeah, why don't you go ahead and elaborate on that?
So if you take the example of the ledger rules again, because it's a nice example, we've written down this mathematical description of what the ledger rules are, and we've stated a few properties of them, and then we've gone and tested things. But so the next step there would be to recast that specification in the language of a theorem prover, and then prove in the theorem prover the properties that we claim to hold, prove that they actually do hold. So, for example, the property that says, the amount of money in the system is constant at all times. You could, in principle, prove that property and have that be known. Not just we've tested that property, but we've proved that property. And that's what a theorem prover lets you do. A theorem prover is a computer program that can check a proof that is written by a programmer. It can check that proof is absolutely true. It's a theorem checker, really. The programmer writes their proof in the language of the theorem prover, and the theorem prover checks that really is a valid proof. It checks that everything has been done correctly. So it means you have to be extremely explicit about everything, right. So which is why it's rather time consuming.
So is that like the Holy Grail? Is that the final step in this process? Would be then proving powerful theorems? Would you say?
Yes, that, and then also, so that would be proving things about the specification, that it has the properties you want. The other thing is trying to establish evidence that your implementation matches your specification. So I said, again, we're doing that by testing.
Right.
But again, in principle, you would like to be able to say that this program proves that this program implements this specification, and that is a good deal harder. We have some approaches that we are working on for doing that for the consensus algorithm. We've been working on that for some time. But it's a as I said, a kind of two-speed approach, and this is the slower, harder one. So we are working on an approach where we can specify Ouroboros in a theorem prover in a process calculus embedded in the theorem prover. Doesn't matter what that is. It's just another calculus. You mentioned lambda calculus earlier. Process calculus is another thing. It's very useful for describing concurrency, and of course, a consensus algorithm is all about concurrency.
Okay.
So yeah, you specify that. You specify that in the theorem prover, and then you try and prove iteratively that each of these kind of design refinements that you make, going from the high level design down to the more concrete design, try to prove that each of those steps are correct, and then finally, that once you get to something that's very, very close to being code, you then have proofs linking that all the way back to your original specification.
Right.
That's our approach, which is a bit of a holy grail.
And so if people are interested in theorem proving, can you throw out some names of packages or initiatives people should look into for that?
Yeah, so this is definitely much more computer science heavy, these things. I mean, especially compared to something like TLA plus. So there are two major theorem provers that have a lot of community support and libraries and packages and whatnot. One of them is the embarrassing French name, the one where they COQ, yes, as I think we discussed this last time, that I think the French academics who came up with this one just wanted the English to have to say it in English, so it's pronounced coq. Okay. So that's COQ because it's the cockerel. Okay. That's its icon, its logo. So that's one theorem prover, coq, and the other one is called Isabelle. And so they're both, in as far as theorem proving is mainstream at all, those are the two major mainstream ones. There's books and tutorials on both of them.
Wonderful. Okay. All right. I think you've given people a lot to think about and investigate. So thank you, Duncan, for spending time to enlighten us. And I wish you the best of luck with all your blockchain work.
Thank you very much.
All right. Take care. Bye.